We're used to rulers that fit our bodies, but nature prefers its own measures. Three constants quietly set the stage: the speed of light, gravity's strength, and Planck's constant. Blend them and you get natural units, including the Planck length, so small that trying to look at it directly would collapse the view behind a tiny horizon. That boundary is a hint that our big and small theories need a handshake we don't yet have. Step out instead. One astronomical unit takes you from Earth to the Sunday. Voyager is far beyond that, with light taking most of a day to make the round trip. The Milky Way spans about 100,000 light-years. Andromeda sits a couple of million light-years away. The oldest light we can see has been traveling for billions of years. The observable universe isn't a wall, just the edge of what light has had time to tell us. Feeling small isn't the same as being meaningless. It's an invitation to keep asking better questions. So how do we actually measure a universe that won't sit still while we fetch a tape? We build a ladder, humble rungs at the bottom, audacious ones at the top, and we make sure each rung overlaps the next. The first rung is as old as Greek geometry: parallax. Hold your thumb at arm's length and blink one eye, then the other. Your thumb jumps against the background. That jump is parallax, and with Earth itself as a baseline half an orbit wide, we can watch nearby stars wiggle ever so slightly over the course of a year. From the size of that wiggle, we get distance. It's the most honest kind of astronomy, pure triangles in the sky. But triangles eventually blur. Beyond a few thousand light years, the parallax shift is smaller than our best instruments can cleanly see. So we climb to the next rung, standard candles objects, whose intrinsic brightness we understand well enough that their apparent faintness tells us how far away they must be. Certain pulsating stars, called Cepheids, breathe in a steady rhythm. The tempo reveals their true luminosity. Compare the true brightness to the brightness we receive, and distance falls out of the arithmetic. With those beacons, we step from our stellar neighborhood to other galaxies. Higher still, supernovae, particularly the tidy explosions of a white dwarf called Type Ia, serve as lighthouses visible half the universe away. They aren't perfect, nothing in nature is, but we learn their quirks, correct for their habits, and treat them with the respect due to fireworks that outshine whole galaxies for weeks. Parallax anchors the candles. Candles bridge to galaxies. Galaxies then reveal something stranger, the redshift of their light, a stretching of every wavelength that whispers. Space itself is expanding. That expansion is a subtle point. Galaxies aren't sailing like ships through a pre-existing ocean. The ocean is swelling between them. It means there's no privileged center, no cosmic capital city everywhere is receding from everywhere else, because the metric that defines distance is evolving. If you imagine dots on a balloon as it inflates, each dot sees all others move away, fast if they're far, slow if they're near. That proportionality speed increasing with distance is what early observers caught sight of in the light from distant galaxies. It wasn't just motion, it was a global rule stitched into space-time. If expansion is the melody, gravity provides the baseline, resisting, sculpting, delaying. Left to gravity alone, the early universe would have slowed its outward rush. Yet the data imply something even more audacious. On the largest scales, the expansion is not decelerating, but accelerating. The universe is not only running, it's lengthening its stride. We give that push a placeholder name, dark energy, not because it's an occult substance, but because it behaves like energy bound to the vacuum, a latent pressure that adds up across the vastness. It is a reminder that our equations can be precise and our understanding provisional at the same time. Between the smallest and the largest, between the Planck length's whispered boundary and the cosmological horizon's quiet circle, lie many clocks. We read them to tell the story of time. At the human scale, tree rings, coral bands, ice layers. In geology, the steady decay of radioactive isotopes, with half-lives that reach calmly across eons. In astrophysics, The lifetimes of stars, which scale roughly as mass to the -3rd power lightweights living for trillions of years, heavyweights burning hot and fast, gone in mere millions. Our sun is moderato, generous, unhurried, a long, golden middle age. Even the sky offers a fossil of its own birth. The cosmic microwave background, the oldest light we can see, released when the universe was a warm fog of plasma and finally cooled enough for atoms to form and photons to fly free. That afterglow is astonishingly uniform, but not perfectly so. Its tiny flex variations of a few parts in 100,000 are the seeds of structure. Those freckles grew, under gravity, into galaxies, clusters, and the filaments we map today. If you ever doubt that small differences matter, remember that every galaxy began as a slightly overdense whisper. The fabric weaves back upon itself. Think of curvature, how mass and energy tell space-time how to bend, and how that bending tells matter how to move. Locally, near a star or a planet, curvature is gentle. Your coffee doesn't spill because Earth curves space, but satellites follow graceful arcs because it does. Around a black hole, curvature tightens until even light must bend its path into surrender. On cosmic scales, curvature may be nearly flat, Euclidean to a remarkable degree, suggesting a balance between the total energy content and the grand geometry itself. Flatness isn't trivial. It's a clue to how the early universe set the initial conditions. We should talk about horizons, because the word is doing two kinds of work. There's the event horizon of a black hole. Cross it, and all future paths, however cleverly plotted, flow inward. But there's also a cosmic horizon, a light cone boundary, the edge of what can have influenced us since the first moment. That horizon is not a wall, it's a history limit. As time passes, more universe becomes communicable. New regions drift into view. And yet, if the expansion keeps accelerating, some galaxies we see today will fade beyond causal contact, their light forever redshifting into silence. The cosmos is generous, but it is not infinite in what any given observer can know. When we say observer, we don't mean a privileged being with notebooks and telescopes. We mean any physical system capable of recording information atoms, grains of dust, a pond surface snagging the reflection of a star. In that sense, the universe observes itself constantly. The mystery is that we are among the observing parts, able to compress what we see into stories and mathematics, to invent rulers that fit our bodies, and then graduate from them toward nature's own measures. There's a humility to the enterprise. We build theories that are spectacularly accurate within their domains, quantum field theory for the small, general relativity for the large, and yet we know they quarrel if forced to share the same throne. Ask a black hole to host quantum fields on a curved space-time, and you can compute astonishing things, like Hawking radiation. Horizons glow, very faintly because of quantum mischief near the boundary. But ask what happens to information when matter falls in and evaporates away and the arguments begin to heat. Does information survive in scrambled form on the horizon? Is space-time fundamentally discrete, with the Planck length acting like a pixel you can never resolve beyond? Or is there a deeper, softer geometry yet to be recognized, one that makes the handshake between our big and small theories not only possible, but necessary? We move forward by triangulation, not only parallax in space, but parallax in methods. We measure the same thing in different ways and require them to agree. The expansion rate, for instance, the present-day Hubble parameter, can be inferred from the early universe patterns frozen into that microwave afterglow, and from the late universe, the distance ladder of candles and parallax. If those inferences differ beyond their uncertainties, we don't merely shrug. We sharpen our instruments, question our assumptions, and sometimes find a crack where new physics could slip through. Disagreement, handled patiently, is a compass. There's beauty, too, in the way complexity emerges from simplicity. Hydrogen and helium, the primal elements, hook together in stars to build carbon, oxygen, nitrogen furnishings for chemistry and life. Those atoms are ejected by stellar winds and catapulted by supernovae into clouds, which collapse again into new stars and new worlds. You're not simply in the universe, you're on your second or third tour, atoms recycled from older suns. When you look up, the sky is not other, it is kin. And if you feel the tug of meaning in that kinship, you're not being unscientific, you're being human. Science doesn't flatten meaning, it refines it. To know that a photon began its journey when there were no continents yet on Earth, to know that we can measure its energy and deduce how space has stretched along the way, that's not a reduction. It's an expansion of our interior horizons. Feeling small is honest, feeling invited is wiser. So where do we go next? If rulers made of Planck, light, and gravity hint at a deeper order, and if the cosmic ladder turns distance into story, perhaps the next rung is to listen rather than look. Light tells us about surfaces and glowing gases. Gravitational waves tell us about the choreography of space-time itself. Black holes colliding, neutron, stars whirling down to coalescence, the slow bass notes of supermassive partners millions of light years apart. Those ripples are rulers of a different kind, calibrated by general relativity, immune to dust and darkness. They pass through matter almost unbothered, carrying pristine news from the most secret corners. And beyond even listening lies mapping, not only the where, but the how much and what kind. How much ordinary matter versus dark matter? What kind of dark energy, steady or evolving? How did the first stars light up the fog? Each of these questions is a way of measuring the same tapestry with new fingers, feeling for hidden weave patterns, a tucked away seam that gives up the garment's design. We stand, rulers in hand, but also metaphors ready, because the world is always larger than any one instrument can capture. Let's take that step out of pure distance and into the symphony of signals that let us weigh, time, and touch, a universe that's been expanding, cooling, and creating for nearly 14 billion years. Listening changes the kind of truth we can extract. Light can be absorbed, scattered, re-emitted, tricked into telling the story of the medium it passed through rather than the source that launched it. But ripples in space-time are stubbornly literal. When two black holes spiral together and merge, the waveform that arrives is shaped by the masses, the spins, and the exact dance they performed in their final moments. Decode the chirp, and you have weighed the unseeable, timed the unclockable, and touched the geometry directly. It's as if the universe sometimes mails us a sealed recording of an event, certified by general relativity, with the contents intact. Those ripples also hand us a new rung for the distance ladder, standard sirens. If the waveform's shape tells us how loud the event ought to be, and the amplitude we detect tells us how loud it was, then the difference is distance. Combine that with an independent measure of recession, often from light, sometimes from the subtle imprint of matter's motion, and we gain a way to measure cosmic expansion that doesn't rely on candles or rulers in the usual sense. It is triangulation across messengers, a conversation between gravity and light that reduces the chance of shared bias. The more ways we can ask the same question, the more confident we can be in the answer. But even listening is not the end of it. There is a quieter messenger that has been with us since the first seconds, the neutrino. These almost non-existent particles slip through entire planets as though the atoms weren't there. In the core of a collapsing star, neutrinos carry away most of the energy, and when they wash over us, they announce the instant the star's heart failed, long before the light of the explosion has fought its way to the surface. If gravitational waves are the drumbeat of the cosmos, neutrinos are the whisper from inside the drum. Someday, when we catch a supernova nearby, in gravity, light, and neutrinos together, we will have a three-part harmony, a full autopsy of a dying sun. Listening, watching, and counting flow naturally into mapping. Consider the large-scale structure of the universe, a delicate, foamy web where galaxies cluster along filaments surrounding vast, underdense voids. This architecture is not random. It is the amplified ghost of those tiny temperature freckles in the infant afterglow. Gravity takes a field of small initial contrasts and, over billions of years, turns it into a stained glass window of knots and strands. By surveying the positions and motions of millions of galaxies, by measuring how their shapes are subtly sheared by the gravity of intervening mass, a phenomenon called weak lensing, we are not just drawing a picture, we are weighing the invisible scaffolding of dark matter. The picture that emerges is cosmology's great plot twist. Most of the matter that dictates the formation of structure is not made of atoms at all. A different ruler appears in that map, the baryon acoustic oscillation, a fancy phrase for an ancient pressure wave that once rippled through the hot plasma of the early universe. When that plasma cooled and the photons decoupled, the ripples froze the same way a sound wave can leave a standing pattern on the surface of a drum when the drummer abruptly stops. That frozen scale, roughly a few 100 million light-years, acts as a standard ruler embedded in the galaxy distribution. Measure it at different cosmic times, and you can recover how the expansion has changed. It is an almost mischievous gift, the cosmos bait to tape measure into its own pattern. Thread these rulers and sirens together, and you get an equation of state for the vacuum, how the pressure and energy density of the thing we call dark energy evolve. Perhaps it is a cosmological constant, simple and stubbornly unchanging. Perhaps it has a history, subtle but real, like the flavor of a tea that deepens as it cools. If the expansion's acceleration is truly constant in its character, the far future becomes a cold, slow loneliness, where gravitationally bound islands, galaxies, and their clusters remain internally alive, but extragalactic light dwindles to a whisper. If the character changes, other destinies are possible. Cosmology here brushes against philosophy, the ultimate weather forecast for everything. Let's return to the notion of horizons, because mapping draws them out of abstraction. There's the particle horizon, the distance beyond which light hasn't had time to reach us. The event horizon, beyond which light emitted now will never reach us in the future if acceleration persists. And the apparent horizon, a local construct that depends on how matter is moving. These are not merely definitions, they are practical boundaries on what questions are answerable. The cosmic microwave background sits just shy of our particle horizon, the earliest surface from which we can receive light. But gravity and neutrinos, which interact differently, carry the promise of even older news. There may be a day when we detect a primordial gravitational wave background, a faint hiss of space-time stirred by processes in the universe's first instance, perhaps inflation, perhaps something stranger. That would be the ultimate standard siren, a ruler laid down before there were atoms. Between the first light and the mature galaxies lies a foggy chapter with a lovely name, reionization. After the universe cooled enough for neutral atoms to form, the lights went dim. There were no stars yet, only darkening gas. As the first generations of stars and black holes ignited, their energetic radiation reionized the hydrogen, breaking electrons free again and making the universe transparent to certain kinds of scattering. Traces of this epoch live both in the glow of the microwave background, slightly smudged by free electrons, and in the shadows of distant quasars, whose spectra carry fingerprints of the last remnants of fog. When we speak of cosmic history, we are not waving our hands. We are reading the marginalia of the universe scribbled in its own book. All these measurements, parallax, candles, supernovae, standard sirens, acoustic rulers, weak lensing, the microwave background feed a single project, to infer the simplest set of principles and parameters that explain the most data with the least fuss. It is not an obsession with austerity. It is a recognition that nature often hides opulence behind concise rules. Newton's law of gravity once unified the fall of apples and the circling of moons. Maxwell's equations put electricity, magnetism, and light on the same stage. General relativity replaced gravitational force with geometry. Quantum field theory turned particles into excitations of underlying fields. Each step reduced the number of assumptions while explaining more. Cosmology continues that tradition. A handful of numbers curvature near zero, a specific mix of matter and radiation, a subtle acceleration, are enough to build a universe that looks remarkably like the one we see. And yet, on the smallest scales, we hear the earlier hint again. The Planck length lurking as a limit, the suggestion that any attempt to measure space-time too finally collapses into a horizon. This is not a failure, it's a signpost. In the lab, we can simulate horizons with clever analog systems, fluids, light in metamaterials, and watch horizon-like physics play out safely on a tabletop. In mathematics, we experiment with space-time as something that emerges from entanglement patterns, as though geometry were a macroscopic description of deeper bookkeeping. Even in black hole physics, a kind of ledger emerges, surface area as entropy, temperature as curvature's whisper, information potentially stored on the boundary, the holographic intuition that the volume story can be summarized on the surface. If that intuition is even partly right, the rulers we have been discussing acquire a new meaning. They are not merely measuring distances, they are measuring how information is arranged. Here is a more down-to-earth thought that cosmology teaches. Precision is communal. No single experiment can lock the cosmos down. A microwave sky map without a galaxy survey is a melody without a baseline. A gravitational wave siren without a redshift is a drum heard from behind a curtain. Parallax without candles stops at the neighborhood. Candles without parallax float unanchored. The confidence arises from overlap, from the refusal to let a single tool carry all our faith. In that sense, cosmology is a mirror for the broader project of knowledge. We are at our best when our ways of knowing disagree just enough to keep us honest, and agree just enough to keep us moving. If you find yourself wondering what this has to do with us creatures who worry about the next harvest, the next job, the next quiet conversation, remember that measurement is a form of care. To measure carefully is to say, this matters, this is worth understanding, this will guide how we live. The same steadiness that times the pulses of a Cepheid star also times a heartbeat in a hospital monitor. The same geometry that bends the path of starlight is coded into the satellite navigation that gets you safely home. The gulf between cosmic and human distances is real, but it is bridged every day by instruments built by hands with their own small rulers. So we climb. We set our baselines Earth's orbit for parallax, kilometer-long arms for laser interferometers, spherical detectors for neutrino whispers, and we read what the universe writes across them. Each rung changes our sense of proportion, but never our right to ask for more. What began with triangles drawn across the sky becomes a network of clocks, scales, and harmonies laid across everything from the first hydrogen atoms to the last red dwarfs. And there is one more kind of ruler we have barely mentioned, time itself as felt by different paths through space-time. In relativity, clocks do not merely count, they participate. A clock deep in a gravitational field ticks more slowly than one high above it. A clock rushing quickly ticks differently than one at rest. We have measured these effects with clocks so precise that lifting one by a few centimeters changes its rate. In that sense, gravity is not just the shape of space, it is the distribution of time. The universe is not a stage where events happen in front of a passive backdrop. It is an active schedule, a living calendar that assigns durations according to curvature. When you absorb that, the Planck length's hint becomes bolder. Perhaps the ultimate rulers are clocks, and perhaps what we call space is stitched together by agreements among clocks about how much time has passed. From here, the next step is natural. If clocks define geometry and information organizes space, then black holes. The ultimate clocks and the densest information vaults are laboratories for the handshake we keep gesturing toward. They force quantum fields and curved space-time into the same room and lock the door. To follow that conversation, we need to look closely at horizons that glow, areas that count bits, and the strange proposal that the edge knows more than the inside seems able to hold. Let's walk to that edge now, rulers in our pockets, clocks in our hands, and see how the cosmos keeps its books. Stand at the brink of a black hole, and the word edge starts to feel inadequate. An event horizon is not a material surface, it's a one-way boundary in the bookkeeping of cause and effect. Light launched outward right at that boundary neither escapes nor falls in. It hovers, red-shifting endlessly, as though time itself were stretched taut. Yet this intangible surface behaves like a very tangible object. It has a temperature, an entropy, and thermodynamic laws. That sentence should make us sit up. Temperature belongs to systems with many microscopic constituents, gas molecules, spins in a magnet, things we can count, at least in principle. If a horizon has a temperature, what are its constituents? What is being counted? The first hint came from trying to keep the second law of thermodynamics safe. Drop a cup of hot tea packed with entropy into a black hole, and naively, the entropy disappears from the world we can access. To rescue the second law, we add a new term. The area of the horizon, measured in Planck units, behaves like entropy. Increase the area, increase the entropy. That inspired a bold formula. The entropy is a quarter of the horizon area in Planck units. A geometry measured in meters suddenly talks like a molecule counter. It's a breathtaking bridge. Then came the whisper that turned into a roar. Quantum fields near the horizon are restless, vacuum not being emptiness, but a seething of fluctuations. From the point of view of a distant observer, those fluctuations arrange themselves into a gentle thermal glow, hawking radiation trickling away energy. A black hole, the ultimate absorber, is also a very faint emitter. Over astronomical times, it radiates away its mass and evaporates. Now the second law is safe, but a deeper law is threatened. Unitarity, the quantum dictum that information isn't destroyed, only rearranged. Imagine tossing a library into a black hole. If the whole later evaporates into anonymous thermal radiation, where did the detailed information go? Was it destroyed, violating unitarity? Or is it encoded in delicate correlations among the outgoing quanta, so subtle as to be practically invisible, but in principle recoverable? This is the information paradox, the modern form of an old philosophical worry. Can reality lose track of itself? We can frame the paradox with a curve. Early in the evaporation, the outgoing radiation looks thermal, its entropy rising. If information is preserved, then at some point the entropy of the radiation must turn over and fall the page curve as more of the black hole's bookkeeping escapes in correlated quanta. Recent calculations, using clever tools from quantum gravity, suggest precisely that behavior. Replica geometries, quantum extremal surfaces, and the idea of islands where part of the black hole interior is counted as belonging to the radiation's entanglement wedge. The math is technical, but the headline is human. The ledger seems to balance. Information is not lost. It is redistributed in a way that defies classical common sense, but preserves quantum honesty. Still, we are not done. One attempt to keep the books tidy is black hole complementarity. No single observer ever sees a contradiction. A distant astronomer says the information is stored and then leaks from the horizon. A falling astronaut says they pass smoothly through with no drama in accordance with general relativity. Both descriptions can be true, provided no one can compare notes in a way that generates paradox. the world enforces privacy between viewpoints. But push this logic far enough, and a sharp objection emerges to preserve unitarity and the smoothness of space-time. Some argue that the horizon must actually be a searing firewall, a wall of high-energy quanta, incinerating anything that tries to cross. That proposal sacrifices the equivalence principle, the bedrock of relativity, for the sake of quantum purity. Many physicists recoil, others keep the debate alive as a productive pressure test. When the foundations disagree, we learn what is indispensable and what can yield. Another path softens the conflict. If horizons have soft hair, long wavelength excitations tied to deep symmetries of space-time, then black holes can carry subtle labels beyond mass, charge, and spin that record details of what fell in. Evaporation can then release those labels in correlations. Or perhaps the interior is knotted to the exterior by quantum entanglement so intimate that geometry itself is a reflection of entanglement, sometimes summarized as ER equals EPR. Einstein-Rosen bridges wormholes and Einstein-Podolsky-Rosen entanglement as two faces of one coin. In such pictures, space-time is not merely a container for quantum states. It emerges from their relationships, like a melody emerging from notes and timing, rather than existing independently of them. Where do we test these ideas? Not by sailing to a black hole with a thermometer, tempting as that would be. We test them in three ways. First, we do precision gravity, measure the ring down of merging black holes with gravitational waves, and compare the frequencies and damping times to the predictions of general relativity. Any deviation, extra overtones, unexpected echoes would be a nudge toward new physics. Second, we image the near-horizon environment with very long baseline interferometry, reading the silhouette and photon rings for signs of exotic structure. Third, we explore analog horizons in the lab, fluids, optical media, superconducting circuits, where horizon-like boundaries generate thermal spectra. These analogs don't prove that astrophysical horizons radiate, but they show that Hawking-like processes are generic. When waves meet horizons, thermality emerges. Meanwhile, theory builds bridges where experiments cannot yet reach. In curved spaces with negative curvature, a playground called anti-de Sitter gravitational physics appears to be exactly dual to an ordinary quantum field theory living on the boundary. This holographic duality furnishes a dictionary. Black hole temperature translates to field theory temperature, horizon area to entropy, evaporation to unitary evolution on the boundary. We don't live in anti-de Sitter space, but the dictionary offers something precious. At least in one fully consistent universe, gravity and quantum mechanics not only coexist, they define each other. That makes the hope reasonable that a similar, perhaps subtler duality organizes our own cosmos. It's worth stepping back to the clockmaker's perspective. Earlier we said that gravity is the distribution of time. Black holes sharpen that idea until it cuts. Time flows at different rates near a horizon. A distant clock watches infalling matter slow, redden, and fade. A falling clock sees nothing special at the boundary, unless of course the firewall camp is right. Which clock should we trust? The answer in modern physics is both, each in its domain. The act of reconciling their accounts, constructing a single algebra of observables that respects both, may be the true heart of quantum gravity. Rulers reduced to clocks, clocks reduced to correlations between subsystems, correlations reduced to entanglement, and entanglement, if the holographic intuition is right, is geometry. Our tools become our ontology. All this might sound remote, a kind of metaphysical athletics held light years from our concerns, but the same entanglement that threatens to tear logic at a horizon is what makes metals conduct and insulators insulate. It organizes phases of matter, stabilizes quantum computers, and underlies the error correction that will eventually make those machines useful. The holographic dictionary turns out to read both ways. Insights from quantum information illuminate gravity. Insights from gravity illuminate strongly coupled materials. The universe is thrifty with ideas, reusing them at wildly different scales. What of singularities, the places where our equations quit? Inside classical black holes, time-like paths end at a curvature singularity. Physics there is not merely unknown, the concept there may be ill-posed. Cosmic censorship conjectures that such breakdowns hide safely behind horizons, protected from the gaze of distant observers. If that protection holds universally, we can do honest science without worrying that naked infinities will ruin our initial value problems. If censorship fails in some regimes near extremal spins, in exotic matter distributions we might glimpse physics raw and unfiltered. Either outcome is instructive. The world will tell us how seriously to take the smooth manifold we draw on chalkboards. Some propose that quantum gravity averts the singularity with a bounce, or transition a Planck star, or other core that halts collapse and over immense times leaks information out. Others suspect that the singularity is not resolved by new stuff, but dissolved by a new description, where questions about subplanckian distances are simply misframed. Remember the warning embedded in the Planck length. Try to make a ruler too fine, and a horizon forms, exiling the measurement you hope to perform. The theory may protect itself from ill-posed questions, in the same way thermodynamics shields us from asking which exact molecule carries the heat across your teacup. While these debates continue, observation races ahead. Gravitational wave astronomy is maturing from detection to spectroscopy. Not just a black hole merged, but its ring-down spectrum had these modes, implying this mass and spin, with no anomalies at the parts per thousand level. Future detectors, longer arms on Earth, constellations in space, precise timing of millisecond pulsars will probe binaries that sing at lower and lower notes. Supermassive black holes, millions of times the Sun's mass, will rumble in slow, rich harmonies, offering exquisitely clean tests of the horizon's behavior. If nature has tucked even a slight deviation into the script quantum hair, delayed echoes, modified dispersion at ultra-high energies, we have a path to hear it. There is a human moral buried in this cosmic account. Confronted with an edge, where familiar rules contradict, we didn't declare defeat. We wrote down what each rule insists upon, and listened for a tune that accommodates both. That's what the page curve work represents, what complementarity and holography attempt, an ethics of reconciliation. Not papering over differences, but formulating them so the world itself can decide. Science at its best is patient about paradox and impatient about sloppiness. Black holes force us to be both. And where does this leave our rulers? At the horizon, the meter stick is less telling than the bit and the tick. A bit counts the alternatives the world can realize. A tick records the order in which it realizes them. Area measures bits, surface gravity measures temperature, and thus tick rates. Geometry, thermodynamics, and information theory conspire to make a single instrument. When you hold that instrument conceptually, if not in your hand, you're not merely measuring a black hole, you're measuring the relationship between knowing and being. Step back once more to the map of everything, the same triad that opened our journey. The speed of light, the strength of gravity, and Planck's constant sits quietly behind every scene we've visited. Light sets horizons and signals. Gravity sets curvature and clock rates. Planck's constant sets the granularity of action, the minimum size of a question the world will meaningfully answer. Blend them to make Planck units, and you get a reminder: our body's rulers are parochial, nature's rulers are constitutional. When you respect those constitutions, paradox becomes guide, horizon becomes ledger, and the night sky becomes not a ceiling, but a living archive. We carry on then, not because we expect the archive to end, but because every new page reorganizes the ones we've already read. The next pages will ask us to thread quantum error correction codes through space-time diagrams, to hear lower bass notes from heavier horizons, to weigh shadows with sharper interferometers, and to translate ringdowns into paragraphs of geometry. The tape is long, the clocks are patient, and the universe is still dictating. Let's keep writing, one measured line at a time. If measurement is our craft, then time's arrow is the workshop's light. Without it, the marks on our rulers would be indistinguishable, the ticks on our clocks unranked. We say that time flows, but physics is choosier with its verbs. The fundamental equations, as far as we can tell, largely respect time reversal symmetry. They permit movies to run backward without breaking the rules. What then fixes the difference between a cup that shatters and a heap of shards that conspires to leap up as a cup? The answer we trust most is entropy, a measure of how many microscopic arrangements correspond to the same macroscopic appearance. Higher entropy means more ways to be the same, and the universe, left to itself, drifts toward the more numerous. This isn't just an abstract slogan, it's a practical guide for books and black holes alike. When you spill ink onto water, the molecules explore more arrangements. When a star collapses, the horizon area our avatar for, entropy expands. But if entropy's increase is the source of the arrow of time, the question is promptly returned to sender. Why did the universe start in such a low entropy state that there's room to rise? On everyday scales, a tidy room reflects human effort. On cosmic scales, our early universe's tidy initial conditions seem to reflect something structural about the way space, time, matter, and quantum fields were set up. Perhaps there was a dynamical process, an early stretch that ironed wrinkles out. Perhaps initial is the wrong word, and what we experience as a beginning is a local chapter of a longer, weirder book. Whatever the answer, the arrow is why memories make sense and why thermometers work. It is the master ledger balancing our ledgers. The arrow governs decoherence, the process by which quantum possibilities become classical facts. A tiny system, say, an atom, in a superposition of two energy levels, cannot help but talk to its environment. That conversation, conducted via stray photons and phonons, entangles the atom with the world, bleeding phase information into a bath of degrees of freedom we neither track nor can practically recover. The result is not that the atom chooses, but that branches of the world emerge in which consistent accounts can be kept. In one branch, the detector clicks, in another, it does not. Our experience is branch-like, not because consciousness has veto power over physics, but because the environment selects stable records, pointer states that survive long enough to be talked about. Rulers and clocks are record-making machines. Decoherence is their quiet ally. Once records are possible, complexity can grow. Entropy rises overall, but free energy, the useful structured stuff, can be tapped locally to build islands of order. Stars form from collapsing clouds, planets condense from disks. Chemistry explores combinatorial space until pockets of self-maintenance appear. Life, in this telling, is entropy's co-conspirator, a delicate mechanism for exporting disorder to the environment while maintaining internal structure. You can literally feel the arrow of time in a warm breeze. Your body's metabolism rides the gradient between sunlit order and infrared glow. So does a coral reef, a city at twilight, a brain dreaming of a solution. All are local borrowings from a cosmic bank whose interest rate is the temperature difference between hot sources and cold sinks. This is why cosmology's large numbers are not mere curiosities. The spaciousness of the universe keeps heat from bottling up. The long lifetimes of stars provide steady power plants. The fine balance between gravity, pressure, and quantum rules lets matter assemble without immediately collapsing or evaporating. Had any of those dials been turned far, the catalogue of possible histories that include long-lived chemistry would have been thinner. It is tempting to elevate that observation into a selection principle, an anthropic shrug. We see a universe compatible with us because we are here to see it. There's sense in that, but we must handle it with care. Used clumsily, it becomes a license to stop asking why. Used properly, it is a boundary condition on curiosity, an invitation to look for mechanisms that produce ensembles of possibilities, and then to understand which members of the ensemble give rise to islands of order, of lungs and lenses and languages. Even without committing to any ensemble, we can trace plausible futures. Stars will keep stitching heavier elements in their cores and flinging them back into the interstellar medium. Over hundreds of billions of years, the bright main sequence chorus will fade, leaving red embers, red dwarfs, to burn long and low. In some far chapter, star formation will dwindle. Galaxies will grow sparse in their exchange of gas. If the universal acceleration persists, the night between islands will deepen beyond appeal. On even longer scales, matter itself may decay. Black holes will evaporate, and the arrows that mattered to us biological, cultural, historical, will have folded quietly into the thermal hush. That forecast isn't a cause for despair. It is a frame within which meaning must be made now, while gradients abound and stories can be told. Stories require standards, not just moral ones, but metrological ones. We have learned to bind our measurements to constants rather than artifacts. The meter is no longer a bar in Paris, it is the distance light travels in a fraction of a second. The kilogram is no longer a platinum lump. It is tied to Planck's constant through a Kibble balance that converts mechanical power to electromagnetic quantities. The second rides the resonance of cesium's hyperfine transition. Newer optical clocks count faster. Ticks in strontium's lattice and push stability so far that lifting one clock by the thickness of a finger changes its rate measurably. Notice the through line. We build our most precise rulers out of invariants of nature and then use them to catch gravity in the act of bending time. Those same clocks become sensors of the world's subtlety. Put a network of them around a volcano and watch the rates diverge as the ground swells. Float them on satellites and macadam into global navigation that corrects for relativity as a matter of engineering routine. Split atoms with lasers and let their matter waves interfere. The pattern is nudged by gravity's gradient, by passing vibrations, by Earth's rotation. These atom interferometers are nascent ears for whispers we once thought unreachable. If you look closely, you can see the grand program marching, from celestial parallax to tabletop phase shifts, from horizon entropy to thermostat readings in a condensed matter lab. One language, many dialects. At the scale of the sky, our maps are becoming orchestral. Arrays of radio dishes listen for the bright 21-centimeter line of neutral hydrogen, tomographing the cosmic web across epochs. Optical surveys tilt the night into a databank, measuring shapes, colors, and flickers for billions of galaxies and stars, cross-calibrated to within a hair's breadth. X-ray telescopes weigh clusters by their hot gas. Gamma-ray instruments catch the tantrums of newborn black holes. Against this polyphony, gravitational wave detectors pick out the low-strings mergers and inspirals, while timing arrays of millisecond pulsars lay out metronomes across the galaxy, hunting for the planetary-scale rumble of supermassive binaries. You can sense the direction toward multi-messenger weather reports of the cosmos, in which a flare in one band starts clocks in others, and the stitched-together narrative leaves fewer places for ignorance to hide. Ignorance does remain, and that's healthy. We have not pinned down the particle identity of dark matter, if it is particulate at all. We have not settled the character of dark energy, if it is truly constant across time. We have not extracted a consensus from the Hubble tension, the persistent mismatch between early time and late time inferences of the expansion rate. Each is an opening rather than a wound. In a discipline as data-rich as modern cosmology, Disagreement is not a scandal, it is an engine. The correct response is not tribal allegiance to one dataset or another, but the design of measurements that interlock, that test assumptions sideways, that are honest about systematics, and that carry their own refutations in their pockets. We spoke earlier of black holes as ledgers. There is a wider sense in which the universe itself is a memory device. Galaxies remember the pattern of the microwave background through their clustering. Stars remember metallicity histories through their spectra. Rocks remember climate through isotopic ratios. Your immune system remembers past infections. Culture remembers the lessons that prove durable. Memory is the thread that makes a timeline a story, rather than a mere sequence of frames. The physics of memory, how to write robustly, how to read without erasing, how to correct errors when noise intervenes, is not parochial to computers. It is the grammar of a cosmos in which information is physical and locality is negotiable. That grammar reaches back to the holographic hints at horizons. If geometry itself is a kind of error-correcting code, as many now suspect, then the reason space-time is so resilient against small perturbations is the same reason a well-designed digital archive survives a scratched disk. The information is redundantly woven. A neighborhood of space can be lost, and the larger code can reconstruct what matters. Translate that metaphor carefully, and it gives us courage. The handshake between quantum theory and gravity may be less about inventing a new object than about recognizing a new organization of familiar ones. We will know we are right not when we've produced a flourish of clever mathematics, but when predictions for observable phenomena ring down spectra, horizon echoes, correlations in the microwave sky, laboratory analogues fall neatly out and refuse to be surprised. In the end, measurement returns to meaning. When we say that feeling small is not the same as being meaningless, this is what we have in mind. The act of placing a ruler against the world is also the act of placing oneself within it. A person is a local, temporary, low-entropy machine that converts gradients into thought and care. A civilization is a distributed sensor network that makes and keeps records. To measure is to vote for a future in which knowledge survives. The constants, light's speed, gravity's strength, Planck's quantum, are not just numbers on a page. They are the cadences of a song to which everything that lasts must learn to dance. So, where do we step next? We have peered at horizons and argued with paradox. We have climbed the distance ladder and tuned our clocks to gravity's rhythm. We have traced the arrow of time from the microwave sky to the warmth of a hand. The next natural move is to ask about initial conditions and emergence. What set the stage for low entropy, and how does structure arise so reliably out of noise? That question threads through inflationary sketches, cyclic speculations, and the physics of phase transitions in the early universe. It also threads through nearer laboratories, through cold atoms settling into order, through materials that remember strain, through fluids that exhibit effective horizons. If the cosmos keeps its books, perhaps the opening chapter is a ledger entry we can still read in the margins today. Let's turn that page together and see how simplicity begets the first patterns that all the rest elaborate. Open the ledger at the first visible entry, and you find a page already half written. A hot, dense plasma, expanding and cooling, initial wrinkles measured in parts per 100,000, chemistry still a notion waiting for cooler days. The natural question is, who wrote the header? In cosmology, that question tends to wear the name inflation, a conjecture that, in the earliest sliver of time, space underwent a brief, furious period of accelerated expansion. Not because space decided to sprint for the pleasure of it, but because a field, call it the enflaton, temporarily took on an energy density that acted like a cosmological constant, driving exponential growth. In a handful of doubling times, any pre-existing clutter is diluted to irrelevance. Curvature flattens, Horizons that would otherwise be far apart are pulled close in the causal past. Irregularities are smoothed away. Inflation is like ironing the universe before the fabric was stitched. Yet the iron left a pattern. Quantum fields can never be truly still. They fluctuate. During inflation, those quantum jitters were stretched from microscopic to astronomical scales, frozen into classical perturbations as expansion outran their ability to communicate. Later, gravity amplified the slightly denser patches into galaxies and clusters, while the slightly emptier patches became voids. That story is audacious. The largest structures we observe grew from quantum noise written across an inflating space-time. If true, a simple mechanism explains uniformity, flatness, and the origin of structure in one stroke. The test is not philosophical consistency, it is statistics. We look for specific fingerprints, near-scale invariant spectra of perturbations, tiny departures from perfect Gaussianity, particular correlations in the polarization of the microwave afterglow. To date, the numbers sit down quietly next to inflation's predictions. The case is not closed, but the book is open to the right chapter. Inflation is not a monolith. It is a family of models, each with choices about the shape of the inflatant's potential and the way inflation ends. That end is as crucial as the sprint itself. When the inflating energy decays, reheating the universe is repopulated with particles and radiation. The details decide how hot the cosmic oven becomes, which in turn sets the stage for early nucleosynthesis, where hydrogen and helium and a dash of lithium are forged in predictable ratios. Those ratios are a remarkable cross-check. Measure them in ancient gas clouds, and you are reading the thermometer settings from minutes after the beginning. Between inflation's graceful ironing and nucleosynthesis' careful cooking, there is room for drama. As the universe cools, symmetries break not because laws fail, but because the favored state at lower energy no longer shares all the delicate balances of the high energy phase. Water doesn't lose the laws of fluid dynamics when it freezes. It simply adopts a lower symmetry arrangement as ice. The early universe likely underwent similar phase transitions in its fundamental fields. When symmetries break, relics can form. Topological defects such as cosmic strings or domain walls, fossils of the way different regions chose different orientations when the choice had to be made quickly. We have searched for these defects in the sky's patterns. If they exist in appreciable numbers, they must be shy, or very light, or very rare. Their absence so far tightens the models. Their possible presence remains a temptation. Another puzzle demands its own ledger entry: baryogenesis, the origin of the matter, antimatter asymmetry. The equations we trust give no built-in preference to matter over antimatter, and yet the world is not made of annihilated light. For matter to win, three conditions must be met in some early epoch. There must be interactions that change the net baryon number. There must be violations of charge and parity symmetries, and the universe must have been evolving out of equilibrium so that microscopic biases aren't washed away. Various mechanisms, electroweak baryogenesis, leptogenesis via heavy neutrino, decays, each propose an accounting trick by which a tiny asymmetry is amplified into cosmic dominance. The proof will be in converging evidence: subtle electric dipole moments of particles, neutrino properties, traces in gravitational waves from violent phase transitions. The story of why something not balanced by its opposite persists at all is still being drafted. Return to the afterglow, that patient, all-sky document. We learned first from its temperature anisotropies. We now learn as much from its polarization. Polarization can be decomposed into E modes curl-free and B modes curl-free. Density fluctuations primarily generate E modes. Gravitational waves from the early universe can generate a distinctive pattern of B modes on large angular scales. That makes the B mode a Rosetta Stone for inflation's energy scale. Detect a primordial B mode and you have weighed the sprint. We have seen B modes produced by lensing, E modes twisted by intervening structure, but the primordial signature remains elusive. The quest is exquisitely difficult. Dust in our own galaxy imitates the signal. Instruments must be schooled to monastic discipline. The reward is outsized. A detection would be the closest thing we have to a photograph of the universe's first instant of pattern making. Patterns don't end with the microwave sky. They cascade into the baryon acoustic oscillations imprinted in galaxy positions, into weak lensing shear maps that weigh the invisible scaffolding, into the statistics of galaxy clusters, whose numbers and masses change with time according to the rules of growth. Each probe presses on the same parameters from a different stance. Change the amount of ordinary matter, and you shift the sound horizon. Change dark matter's smoothness, and you alter lensing's power spectrum. Change dark energy's character, and you change the timing of structure's assembly. It is the parallax of methods again. Distances, growth rates, and light cone effects triangulating the same geometry. Amid all this, it's easy to forget how much of our confidence comes from the narrowness of the viable. Tweak the slope of the initial perturbation spectrum too far, and small-scale structure either never forms or forms too eagerly. Tweak the helium yield, and you complicate star formation chemistry. Tweak the expansion history, and you upset the neatly stacked rungs of the ladder. The fact that a handful of numbers matter, density, baryon fraction, amplitude and tilt of primordial fluctuations, optical depth from reionization, Hubble parameter fit so much data is not a conspiracy. It's a triumph of the strategy. Choose the simplest sufficient model and let the anomalies define the next questions. Here, emergence enters not as a metaphor, but as a roadmap. Consider how order arises from noise in nearer laboratories. Quenched cold atoms in optical lattices relax into phases whose low-energy behavior can be captured by elegant, effective theories. Blind to the grubby details of individual collisions, quark-gluon plasmas created in heavy ion collisions behave like near-perfect fluids, their viscosity brushing against conjectured lower bounds. Certain materials, strained just so, produce quasi-particles that behave like relativistic fermions with tunable speeds of light. Each case whispers the same lesson. When many degrees of freedom cooperate, universality appears. Different microscopics, same emergent law. Cosmology is the largest stage for that principle. We do not need to know every pre-inflation micro-fact to predict the spectrum of ripples. We need the few features that survive the washing machine of emergence. That is why the error correction analogy is more than decoration. In holographic models, bulk geometry is encoded redundantly in boundary degrees of freedom. Lose a patch of the boundary and the bulk can still be recovered. In our world, redundancy rides on physical processes, multiple, independent records of the same event. Light echoes in dust, gravitational imprints in motions, chemical memories in isotopes. Decoherence doesn't merely suppress quantum interference, it writes copies of classical facts into the environment. Reality is robust because it is overwritten everywhere. Once you see that, the conceptual distance from a holographic code that repairs erasures to a cosmos that forgets small errors on the way to large truths shrinks. What about the beginning itself, if that word is even apt? Inflation coyly defers the question. It explains the observed initial conditions by dynamical smoothing, but it does not say what lit the inflaton's fuse. Some proposals push earlier, quantum cosmology scenarios in which the universe tunnels from nothing, or where time emerges across a bounce from a prior contraction, or where there is no singular beginning, but a past eternal inflationary sea, in which pockets like ours thermalize. Each faces deep questions about measure how to count infinities. without fooling ourselves, about initial entropy, what sets the low entropy boundary that makes the arrow meaningful, about predictivity, which features are inevitable rather than optional. The scientific stance here is not to pronounce metaphysical verdicts, but to sift for observables. Relic gravitational waves, non-Gaussian scars, isocurvature modes, defects, tiny failures of consistency relations. If the opening chapter is etched into the margins, it is our task to learn how to read marginalia. Closer to home, the same logic of emergence tells us why life and mind are not intrusions into physics, but its fluent expressions under particular boundary conditions. A biosphere is what you get when a planet enjoys steady energy throughput, liquid solvents, and chemical building blocks. A mind is what you get when a biosphere stumbles on architectures that model the world well enough to preserve themselves. None of that cheapens meaning. On the contrary, meaning is what it feels like from the inside, to be a system that writes, reads, and edits records in a universe whose arrow of time points downhill. Culture is the long experiment whereby such systems refine their rulers, moral ones, metrological ones, and decide which records to keep. If we return, finally, to the human-scale toolbench, the continuity is striking. The constants that starred at the outset, light speed, gravity strength, Planck's constant, recur in the calibrations of our best instruments. Optical clocks compare tick rates across mountain valleys and infer geopotential maps. Interferometers trace femtometer path differences to hear the ring of horizons. Radio arrays correlate nanosecond timing across continents to sketch a photon orbit near a black hole. Each technology is a bridge, from tiny controlled systems to stupendous uncontrolled ones. We do not dominate the cosmos. We couple to it with care, and it answers. So the ledger's early pages are not sacred, they are testable drafts. Inflation may be right in broad strokes, but wrong in detail. Dark energy may be constant today, but not forever. Dark matter may be a new particle, a family of them, or an emergent phenomenon of fields we haven't named. The right attitude is crafted curiosity. Build experiments whose null results are as informative as their detections. Design cross-checks that humiliate our favorite stories if they stray. Welcome tensions as beacons rather than embarrassments. The universe has been astonishingly forthcoming when asked the right questions with sufficient patience. Where do we point our rulers next? Toward the faint hiss that an early phase transition might have left in the gravitational wave background. Toward the B-mode curl the sky may yet confess. Toward direct detection of dark matter interactions in laboratories, quiet enough to hear a whisper from the galactic halo. Toward surveys that watch billions of galaxies evolve in slow motion, disentangling growth from expansion. And, because humility is a strategy as well as a virtue, toward the tabletop, where analog horizons and emergent geometries can be probed until the metaphors either fracture or harden into principles. If there is a single lesson running through this arc, from Planck rulers to parallax ladders, from black hole ledgers to inflation's ironing, it is that simplicity begets fecundity. A sparse set of rules, applied and reapplied across scales, yields an orchard of phenomena, most of which are not obvious from the seeds. We live in that orchard. Our task, modest and grand, is to keep learning which fruit grows where, which branches entwine, and how the sun that feeds it all first rose. The page ahead will ask us to tie emergence even tighter to information, to see whether space-time itself can be written as a code whose error syndromes we can, in principle, diagnose. If that is right, then the opening of the book is not a singular line, but a construction manual, and the universe's meaning is inseparable from its capacity to remember. Shall we turn that page? Turn the page, and the blueprint sharpens. Information, not as metaphor, but as the fabric from which geometry is cut. The modern hunch is audacious yet disciplined. Space-time behaves like a quantum error-correcting code. In ordinary error correction, you encode a fragile message across many degrees of freedom so that local noise can't ruin it, lose a piece of the storage, and the message is still recoverable from the rest. Translate that to gravity, and you get a striking picture. Bulk geometry, the inside of a region, can be reconstructed from suitably large patches of the boundary data. Lose a small slice of the boundary, and the bulk barely notices. That redundancy feels like the reason space-time is so sturdy at macroscopic scales. Perturb a few qubits of reality, and the geometry heals. You can see the scaffolding in toy models built from tensor networks, webs of entangling gates that map a lower dimensional set of quantum degrees of freedom onto a higher dimensional emergent geometry. Diagrams like MERA, multi-scale entanglement renormalization ansatz, don't just compress ground states efficiently. They look uncannily like discrete hyperbolic spaces, with radial depth behaving like resolution. Coarse features live near the boundary of the diagram, fine features sit deeper, and the network structure enforces a kind of radial protection. Bulk operators can be reconstructed from many overlapping boundary regions. That's an error-correcting property drawn as geometry. In continuous language, the same idea arrives via holography. A gravitational theory in a volume can be exactly dual to a quantum field theory on the volume's boundary. The dictionary is technical, but several entries glow with meaning. Entanglement entropy of a boundary region is given at leading order by the area of a minimal surface in the bulk that anchors to the region's edge, the Ryu Takayanagi and Hubani-Rangamani Takayanagi prescriptions. Area measures entropy again, boundaries keep books on interiors, and the network of minimal surfaces stitches a metric out of information theoretic primitives. In that sense, distances in the bulk are summaries of how much entanglement the boundary needs to represent correlations between its parts. Space is not the stage, but the summary statistic of quantum relationships. This reorganization of ideas changes the valence of ancient puzzles. Take the black hole ledger. If geometry is code, then the where of information is not a simple address. Data about the interior can be encoded non-locally across the boundary. Disturb one corner and you learn nothing. Assemble a large enough share and the message decodes. That is why the islands we mentioned earn their keep. The portion of space you must count when you compute the entropy of radiation is not naively outside only. It can include interior patches, because the encoding ties those DOFs to the radiation's algebra. The page curve's turn is the moment the code flips its most efficient reconstruction from mostly in to mostly out. Notice how redundancy quietly carries the metaphysics. Reality becomes robust not because it is hard, like steel, but because it is overwritten, like a good archive. Decoherence writes many copies of classical facts across the environment. Holography writes many ways to reconstruct the same bulk operator from different boundary wedges. Error-correcting codes ensure that local losses don't destroy the global message. The arrow of time is then not only the growth of entropy, it is the growth of records, the steady increase in the number and distribution of copies that stabilize a history. That's why classicality blossoms, that's why memories endure, that's why meaning can be negotiated at all. Inside this framework, complexity steps forward as a second ruler for time. Entropy counts how many microstates fit a macro description. Complexity estimates how many simple operations gates you need to build a given state from a reference. For many closed quantum systems, complexity is expected to grow linearly for an astronomically long stretch before saturating, even when entropy has already plateaued. Gravity seems to know this. Certain conjectures tie the growth of wormhole interiors to the growth of state complexity. Complexity equals volume or complexity equals action. After a black hole forms and settles, its horizon area, and thus entropy, stabilizes quickly, but its Einstein-Rosen bridge keeps lengthening for a very long time. It is as if the interior keeps time by complexity. The ledger's pages keep being written not by adding more bits, but by composing the existing bits into ever more intricate sentences. That view reframes scrambling. A black hole is a fast scrambler. Throw in a diary, and in a time that scales like the horizon radius times a logarithm of its entropy, the information is chaotically dispersed across its degrees of freedom. You cannot recover the diary from a few qubits. You'd need access to a macroscopic fraction. Yet, in principle, after the page time, the diary can be decoded from the Hawking radiation if you also have a quantum description of the remaining whole. The Hayden-Preskel thought experiment makes it crisp. Past the page time, new infalling information becomes mirrored in the outgoing radiation rapidly. Because the joint system's state is so thoroughly entangled that small outputs carry surprisingly rich correlations if you hold the right decoding key. In the code picture, that key isn't a magic password. It's the insistence that the encoding is global, and that typical states hide structure locally, but reveal it in the right cross-sections. There is a practical moral here. When we say information is physical, we don't only mean bits heat up your laptop. We mean geometry, causality, and locality are emergent constraints on how information can be encoded and decoded. The speed of light is a limit on signaling. Horizons are limits on which subsystems can participate in a reconstruction. Curvature is a statement about how decoding regions must grow to grasp a given bulk point. From this angle, the constants with which we began, light speed, gravity's strength, Planck's quantum, are not merely conversion factors. They are guardrails. The universe places on the information processing it permits. Shift from black holes to the cosmic web, and the same grammar persists. Growth of structure from initial noise is an error-correcting saga. Gravity takes blurred, redundant initial records, tiny acoustic ripples, quantum stretch perturbations, and coarse grains them into durable macroscopic features, filaments, halos, voids. Different microrealizations lead to the same macrostatistics in universality again. Weak lensing then reads those statistics back out. Light from distant galaxies is sheared and magnified by foreground potentials. And by accumulating many noisy measurements, we reconstruct a cleaner map redundancy turned into signal. Every step is a trade between compression and fidelity, between losing irrelevant detail and protecting the salient message. The fact that a 6-parameter model summarizes a sky full of galaxies is not anti-romantic reduction. It is a testament to how much of the universe's long story is written in repeatable strokes. Return now to initial conditions with this lens. Inflation's job, in code language, is to prepare a state that is easy to protect. Nearly Gaussian, nearly scale-invariant fluctuations with small, well-structured deviations. Such a state is maximally compressible. Its information content per mode is low, yet it seeds an extravagant future after gravity amplifies some modes and damps others. That economy is why the microwave background encodes so much in so few numbers, and why baryon acoustic oscillations survive as a standard ruler across billions of years. The early code wrote big, clear watermarks into the sky. If information and geometry co-determine each other, then thermodynamics gains a fresh gloss. The first law in black hole mechanics connects changes in mass, area, and angular momentum. Hawking's insight supplies the temperature, and the generalized second law insists the sum of outside entropy plus horizon area never decreases. In code terms, that second law says the recoverable message about the exterior plus the redundant encoding cost at the boundary is non-decreasing. You can spend one to gain the other, drop entropy in, horizon area grows, let the whole radiate, exterior entropy grows as area shrinks, but the ledger stays honest. This isn't poetic fancy. It is a consistency condition tying microdynamics to macro bookkeeping. What does any of this buy us on Tuesday's Outside Thought experiments? First, it guides instrument design. If locality is emergent and information is robust only when redundantly recorded, build instruments that make many independent copies. Time delay interferometry in space-based gravitational wave detectors. Multi-band, multi-epoch surveys that cross-check lensing, clustering, and supernovae. Quantum sensors that distribute a phase record across entangled atoms to resist noise. Second, it informs data analysis. Look for error syndrome patterns, cross-correlations that reveal whether an anomaly is a sky feature or an instrumental ghost. Third, it fertilizes cross-disciplinary moves. Techniques from quantum error correction sharpen our understanding of turbulence in strongly coupled fluids. Holographic bounds inspire new inequalities for entanglement in many-body systems. Conversely, condensed matter dualities suggest emergent gravities in lab-sized arenas, letting us rehearse horizon physics without a singularity in sight. There's also a cultural dividend. A civilization, viewed thermodynamically, is a machine for sustaining low-entropy islands by exporting heat. Viewed informationally, it is a machine for making, copying, and error-correcting records. Libraries, observatories, legal systems, rituals, each is an encoding scheme that keeps certain invariants stable while local noise, forgetting, bias, accident nibbles. To practice science inside such a civilization is to refine those encodings, define units from constants, intercalibrate instruments until they agree to disagree within quantified bounds. Architect archives that future readers can decode without our context. When we measure a B mode or time a pulsar, we are not just extracting numbers, we are strengthening ligatures between disparate records so that meaning won't tear under strain. Does the code picture answer everything? Of course not. It moves questions. What is the microscopic substrate that plays the role of qubits for our universe? Are the gates fundamental interactions, or is gate language already an emergent, high-level description? Why do the codes we glimpse seem so good at protecting locality, given that quantum mechanics treats non-local superpositions as cheap? And how does complexity growth intersect with the arrow of time in open systems, those like us, awash in flux, not sealed in Hilbert space jars? Each is an empirical challenge in disguise. Listen for horizon echoes, chase primordial waves, map cosmic shear with fewer systematics, build quantum simulators that cross the toy model gap to honest dynamics. If this all sounds like an ode to restraint, that's because it is. The universe's most extravagant spectacles, supernovae, merger ringdowns, the cosmic web, are legible because simple organizing principles police the riot. Entanglement organizes geometry. Redundancy stabilizes records. Complexity keeps time when entropy is bored. Our rulers meter, sticks, clocks, sirens, standard rulers carved into galaxy maps are therefore not parochial tools, but interfaces between levels of description. Each interface is a contract. If you give me these clean inputs, I will give you macroscopic laws that don't care about the ultraviolet mess. We can end this page with a pragmatic vow. Keep building rulers that talk to nature's constants. Keep designing experiments that overlap on purpose, so that no single method can deceive. Keep translating between levels micro to macro, code to geometry, until explanations shorten and predictions lengthen. The next natural move is to bring this down one notch further, from universal architecture to local habitats. How do these principles inform the stability of planetary climates, the longevity of biospheres, the windows of habitability around different kinds of stars? How do gradients, redundancy, and error correction play out in the chemistry of life and the architectures of minds? If space-time is a code and black holes keep ledgers, then a world like ours is a running program on that substrate. Let's open the console on that program. energy flows, chemical cycles, climate feedbacks, and see how cosmic bookkeeping sets the bounds for living archives like oceans, forests, and the stories we tell.